Hi, Srini. How are you? Cut your hair.
Hello?
Cut your hair, is it?
Long time, sir.
Long time already, ah? Okay, I just
2
saw
weeks
today.
already.
So, clean cut. How are you?
I'm fine. Oh, sir.
Yes.
Did you know they delay school 2 weeks, teacher?
Say again.
They delay school 2 weeks.
Oh, delay school another 2 weeks, ah? Why?
Instead of March 20, March 21, I'm supposed to go back, right? So correct.
Mm.
I'm going back at April 4.
Why did they delay?
I think cases, Sally, they say all the secondary school, including Form 6, 2 weeks online class.
Oh, online classes, ah. Okay, lah. They are worried
I
about
mean,
the
still not
number of
going school,
cases.
lah.
They are worried about number of cases increasing, ah.
So that means from today, I got 1 month of not going to school, lah, sir.
Yeah, so you will have more time for you to do your homework, okay? As I say, there is no shortcut, lah. Right? All the video is already given you. I don't know why you ask me to teach you again. Yeah, wasting money.
Okay. Then we do the SEM 3 one, lah, sir.
Do what?
The SEM 3 one, continue.
SEM 3.
Continue, lah, sir.
Continue. Don't to have anything to ask.
No, lah, sir, since you say like that, I'm not fully ready to ask yet, so might as well go.
You want, I can teach you, no problem. It's just that it's a waste of money. It's better for you to go over it and then try the focus question. You can't study.
No, not yet.
You are trying to do is study physics. You can't study physics, right? You have to study it and do the focus question to make sure you understand and know how to apply. And then force in the formula. That's the important thing. Because there's too many formulas. You don't learn, you will be lost. That's why it's happening. So far, what you're doing is you are going to hit or miss. Hit means you study, it come out, you pass. So if it doesn't come out, then you fail. That's why there's not the way to study physics. That's what I did also when I was in university. Because no one to help me. So I also struggling because no time to study. Staying too far away from university. Traveling take a lot of time. So university, you don't learn to look into textbook and learn yourself. You go to university, you will struggle because university there's no more tuition. Nobody to help you already. Right? Because the syllabus hard to find a teacher to help you lah. Because the syllabus is depend on the lecturer himself.
Oh, you mean find a good lecturer and then ask him to teach?
Yeah. Only STPM you can find because there is enough student to teach. University, the syllabus is completely different. Each university have their own syllabus, and the number of students who need tuition is very few, very hard to find. So who want to major in that? It's a waste of time. A-level, that's why you cannot find STPM lecturer. Most of them will prefer to go to A-level because A-level is the bulk of the student. About them to make money. STPM, very few students do tuition. Okay, in that case, let me close all the thing. I thought you want me to teach you, then I will teach you, no problem. I think we are to sleep. Okay.
I think we are what? Sure.
Yeah, on a Young's double sleep.
Oh.
Okay. Am I in the right place or are you seeing the slide now? Wave optics?
Yeah, I'm seeing the slide now.
Okay, tell me if you can't see that. Okay, we are now in a two-slit interference pattern, 23.3. Right, that's the reference book. page 160. I organize differently, that's all. Here's your syllabus. Explain Young's two-slit interference pattern. Then you're supposed to derive the formula. Right? This is for fringe separation X. Then after that, interference in thin film. Explain the phenomena of thin film interference or normal incident light and solve related problem. Okay. Requirement for interference. Two sources must be coherent. Right? That means the source that send out the wave must have a constant phase relationship. So that the requirement is they must have the same frequency or wavelength. Same speed, same amplitude. This is because you want destructive interference. Right? You want when the light interfere, you want it to be complete dark. You want a little bit of light. That's why you have to be same amplitude. Same type and plane of polarization. Right? I thought we have covered some part of this. Am I right or wrong?
Yeah, we did.
Where did we stop? Any idea where did we stop?
Go next one, sir. I think we stopped at slide 9. Slide 9. Yeah.
Are you sure?
Yeah, I remember you teaching me this that day.
I thought we have covered more than that. It's okay. If you forgotten, we can go over, no problem. Right, it is the white slit or white aperture. Right, the aperture is white compared to the wavelength. Then the diffraction is small. Diffraction is small. So that region of interference, remember, the wave from here and the wave from here interfere in this region only, not outside. Here only one wave. Here only one wave. So they don't interfere, only here only. We can find the pattern here. Right? This is called the double slit. Right? And then the distance between the bright to bright peak is your Y. Maximum intensity to maximum intensity, that's why it means like bright peak. Then, if the slit is narrow, the diffraction is greater, and that region is larger. Right? As I say, the fringes are more here, less here. Right? So comparing a wide slit, this is a wide slit, and a narrow slit is a narrow slit. The fringe are found only in the region of interference. That is a smaller region, that's a bigger region. Where the slits are wide, the diffraction is small, diffraction is small. The region of interference is also smaller, and thus less fringes are observed. Right? It is narrow, diffraction is large, region of interference is also large. And characteristic of interference fringes, should be able to recognize. This is the intensity distance graph. Right? We measure from here. Here's the center one. Right? The center one. Here is center one. And the brightness of each one is the same. Right? Intensity of each band is the same. Threshold of human vision causes a normal position to appear as a dark fringes rather than a dark line. Right? By right, this one show you only one dark line there, dark line there, dark line there. But because of threshold of vision, it means that the eye cannot distinguish at a certain intensity. The eye will say it's completely dark, even though there's a little bit of light intensity. Okay, so that's what I mean by threshold of human vision. So that means that instead of seeing dark line, we see dark band. But our Y is from peak to peak, right? Maximum intensity to maximum intensity. That's why when you measure it, you observe this pattern, you want to measure Y, you don't know where to measure. Where's the center? Where's the center? So there is a bit of uncertainty. And then X is also small. Okay. Explanation. S, this is S, this S1, this S2 are point sources. A slit is a line of point sources. Parallel rays, right? Here, parallel rays will fall on the slit S, and because this is a point source, it gives out spherical wave. The broken line is your trough. The dark line is your crust. Right? They are using Huygens principle to explain. So the single slit is the size of the wavelength. There's single slit. Diffract, the incident monochromatic light. This is monochromatic. Right? The parallel rays coming in, monochromatic waves, and then this becomes circular wave. Wave leaving the double slit, so are from the same wavefront. Right? You look at the wave there, this point there, S1 leaving, right? The point source leaving from the wavefront here, and from the same wavefront, the S2 and S1 are from the same wavefront. Right? And remember, they are very small, size of a wavelength, so you can consider as a point source. Or another way of saying is division of wavefront. Right? It is taken from the same wavefront. That's how we make it coherent. Coherent wave leaving the double slit. So that's how we make it coherent. Coherent leaving S1 and S2, they are in phase, and then they are diffracted, and interfere in the region of interference. And then we find the pattern here on the screen. Right? We see bright, dark, bright. Same on the other side, dark, bright. Okay, now in this region only, region of interference. Okay, so that is required for your worksheet, number 21, B and C. What is coherent? Okay, you can get for internet. I just try to show you. Internet try to be colorful, but you have to be careful. Right? You cannot have a light source like that and then have interference. You have to put a lens there. Make sure that the ray coming out is parallel. Right? That's your worksheet 19C. So the wave coming out from S1 and S2, where there is no path difference is 0. That means they travel the same distance. So there is a path difference of 0. So we call that M0, constructive interference. And then you have another one. Right? The first destructive interference is occur at path difference of lambda 2, lambda or half lambda. Right? At the screen here, remember it's traveling. Right? This one just show you the 0 and the 0 there interfere. Right? And the crust and trough will interfere as the wave move along. Okay, you should be able to number it, to label it. Here, from S1 and S2 to the screen is displacement distance graph. On the screen, we observe displacement time graph. Right? The first one at the center one is called the central bright band or center bright fringe, where the path difference is 0. And then the first one on this side, on the other side, is called the first bright band. Path difference is lambda. Okay, this is just repeating. You must be able to label. This is using Huygens principle to explain. So the central bright band, the first bright band, right? The first bright band. Also on the other side, you can call this positive, this is negative, also can. No, it's a choice. Okay, so in this case, if it's constructive, The path difference is 0, lambda, 2 lambda, 2 lambda will be up there, 2 lambda, that will be down here. Then for dark band, that one, dark band there, right? The first one will be half lambda, path difference, half lambda. So this will be half lambda. This part will be half lambda. Okay, so you should be able to label path difference 0, path difference lambda, path difference lambda also. Right? Destructive, the first one is half lambda. The other side is half lambda. Okay, any comments so far? Anything not clear? Okay, I just redraw that using
So
usual
far,
principle.
okay.
Right, I'm just redrawing this part. Then make sure you know how to label. The center is here. Right? Center, straight line, perpendicular bisector there, draw here. That's the center one. Right? I'm just cutting here, that's all. Putting it here. Make sure you know how to label. Right? There's the center one, 0. There's a 1, 2, 3, if we consider M. Right? Path different, this will be 0. This will be lambda, this is 2 lambda, this is 3 lambda. Right? General equation is M lambda. M is 0. 0 is here. 1 is here. 2 is here. Dark fringe. Dark fringe, we start from 1. Right? There's no 0 there. We start from 1. So half is here or here. Either way. Right? This one is 1.5. This one is 2.5. Right? And that's the general equation. M minus half lambda. M is 1, 2, 3. That's 1, 2, 3. 4 is here. Okay, remember going over with you already, but since you say haven't. Okay, R and S are in phase. Intensity at P is 0. If R and S are 180 degrees out of phase, what is the intensity at P? Yep. If they are in phase at P, maximum intensity, sorry. R and S are in phase, intensity at P is 0. Okay. Intensity at P is 0. Now, if R and S is same diagram, but they are 180 degrees out of phase, the source here. So what is the intensity at P?
Maximum. They're not maximum, sir.
Let me just go through and see what I've done something wrong. R and S are in phase, intensity at P is 0. 180 degrees out of phase. Oh, correct. Maximum. Why? They have put minimum. Right? 180 degrees phase difference is the same as a half lambda. So if this is destructive, this must be constructive. Then it's maximum intensity here. Right? You must know roughly the size of the different value. Right? Your capital D from top here to the top here, D or from center to center lah, about 0.5. I think your book, I don't agree lah. Right? A is usually about 0.1. You can't make it smaller than that. And that double slit to screen is capital D. It's about 2 meter or 1.5 meter. Wavelength of visible light is 390 to 780. Your book is also wrong in this area. And then your X or your Y, that's your fringe spacing. So we can take an example and calculate out. That formula you need to memorize. Okay, your book use that as A. Okay, I use D because it can be very confusing. A is not the slit size here, right? Which they use as slit size in our next topic. Okay, so I use 400, right? 400 as the wavelength, and D I use 2 meter, and then D 0.5 change to meter, I get 1.6 mm. Right? You can see it's very small, very hard to measure. That's why you have to use the vernier. And there's a lot of error here. Okay, for a wavelength of 600 nanometer, how many wavelength is there in this aperture? Right? Remember our theory for Young's double slit is that this must be the size of the wavelength, but we cannot get the size of wavelength. Use A 0.1. So how many wavelength is this one? Calculate and tell me. Ken? How many wavelength is this one?
6 times 10 to the power -3 meter.
Okay. -3. How do you get that? That one?
Oh, you know the 0.1 above, I put it down, and then the 600, I put it above, I did it
No,
opposite.
this is longer, this is shorter. Right? The wavelength is shorter, so you want to see how many wavelength are in the long there, like how many division are there. Right? So that one change to meter. Cannot afford that carelessness. That one, 600, change it, 600 nanometer, change it to meter. So it's 167 wavelength. Okay. Right? Worksheet 1819. Okay, let's derive the formula. Right? Let's focus on this triangle. Right? Remember, there's your XM, there's a center reference to the M maximum. We call the distance as XM. And that distance is D. Right? Remember, D is very large compared to this angle. So this angle and this angle is roughly the same. Okay, we just assume it's approximation. Right? S2N is distance, which is the same as that one. It's a path different. S1P and NP, right? They are same distance, except this one has to travel extra that distance there. If you want construction interference, this must be your M lambda. Okay, the path difference must be M lambda. And if you look at this triangle, right, that delta there is just your D sine this angle. That's what we get here. And that must be M lambda. Right? And then we can take our D down. That's what we do. Take a small d down, cross multiply, we get this M lambda D. Okay, let's just continue. Now we focus on this triangle. The angle is theta. That's XM. That's your D. So we use tangent XM over D. Right? For small angle, these two are the same. Right? Remember, our theta is small. So tangent theta equals sine theta. These two are the same. We can take our D across there. Right? Capital D across there, we get the equation. Now we go to the next one. This is M. The next one, M plus 1. M plus 1, and just replace this M with M plus 1. No? And then we subtract. Right? The subtract this one will be X. No? Okay. So this M lambda D times D is M lambda d times d. We are still leave with this one. Right? Lambda d over small d times capital D. That is the one. That's your x. That's how we get our x. Anything not clear?
So far, okay.
Okay. Right? If you remember, there's a lot of fringes there. We call this one xm. Then the next one will be your xm plus 1. Just illustration only. Right? This is a poor illustration. If we call this one xm, it can be a lot of them there. And the distance is x. That's all. Factors affecting interference pattern. Right? We look at these two equations, that's all. This one, sorry. This one and this one. Intensity is inversely proportional to distance squared. All these parameters you must know. Right? What do they call? Fringe spacing, screen slit distance. Okay. That one is your capital D. That one is a small d. From center to center. Slit spacing, your book called A. Wavelength. Right? That's your light source, wavelength lambda. Effect on X. Right? Must be able to read this equation. D increases, X increases. Band widens, brightness decreases. D increases, this one, small d, decreases. And X must increase. Sorry, this one increase, this must decrease, X must decrease, sorry. Lambda, as lambda increases because it's proportional. Right? If we use blue light as a shorter wavelength compared to red light, so if we change from blue to red, then blue light has a narrow fringe spacing compared to the red. Okay, you must know all this term. This is your worksheet number 17. I hope you have print out your worksheet. If not, you are the one losing out. Okay, and this one is your worksheet 20A. Double slit, single slit distance, that distance. This is your double slit, that's your single slit, that distance. I call it S. If you decrease it, that means you are bringing this source nearer. You are increasing the intensity, that's all. Increasing the intensity. So you are increasing the energy here. So your brightness of the fringes will increase. Right? That S there is not in this equation. So it doesn't affect your X, the distant X. Widening the single slit. The single slit, make it wider. When you widen it, you allow more light to pass through. Right? Increase the brightness, more energy pass through, more. Increase the brightness of the fringes. Same. It doesn't affect the equation. Right? Because the A here doesn't come in here. Except, always remember, further widening will cause the image to be blurred. Right? It's no more a point source now. It's many point source. Right? We want a point source. That's why we want a narrow slit. But when you widen it too far, too wide, it's no more a point source. It's many point source. Then you have a problem. It become blurred. Right? Source become incoherent. Okay. If you use a point slit, to the double slit as point, then you see point image. This is for point sources. This one is for if you use slit, double slit as slit. See, they have the same distance and it doesn't change. Point source will give the same fringe system. But slits, line of point source, give brighter fringes. by reinforcing the pattern. Okay, this one light, 1 point source only. So you got a lot of point source, you will see it brighter. Right? You don't need to know this equation, so don't bother about that. It's not wrong if you introduce it. Okay, sometimes I use X, sometimes I use Y. Wavelength increases, Y increases. Right? Remember, your wavelength is inversely proportional to frequency. We use C equals to F lambda. C is always constant. Fringe spacing for red light is greater than for blue light. Right? Red light, longer wavelength, that one is bigger. Right? That's what it means here. The brightness of band is constant. Right? Let's compare. That's for your blue or violet. Okay, that one compared to the red one, this one is bigger. Right? The fringe spacing is bigger. And brightness is greater for here. Right? Brightness is greater compared to the red one. Okay, for the simple reason that when you have this one, you stretch it out to a bigger area, then you get the red one. Right? That means the energy is distributed over a bigger area, the intensity becomes smaller. No? It's called band widening. Right? Longer wavelength, longer Y. Shorter wavelength, shorter Y. Can use violet or can use blue, the same thing compared to the red one. Okay, that's why I say same intensity falling on this band, but because of larger area here, the brightness is less compared to your violet band. That's all. Right? Increasing D, I always go to the formula. Increasing D, increase Y. Because Y is proportional to D. Brightness, increase your D. Remember, this R is the same as your D. Right? Increase your D, you decrease the intensity. So brightness decreases. Slit spacing, which is A or D here. Increasing D or increasing this one, Y becomes smaller. Right? Because Y is inversely proportional to D. Brightness remains the same. Right? It doesn't affect your distance. Keeping D constant, right? Or that A constant, but increasing the width of the slit. Right? Yeah, this one we have gone over already. Increase the slit, you allow more energy to pass through. Thus, will be brighter. Y is not affected, right? Because you don't change D or you don't change this A, don't change this D. Y is always the same. Except as you increase Y, it becomes blurred. That's all. Right? If you use white light, same. Center fringe will be white as all colors interfere. That center one will be white. Right? But because of different fringe spacing, right? You will see the red one here at the end there. Violet you probably won't see that because all the color will interfere in the white one. Right? So these are rainbow color there. Higher one harder to describe. Right? So the center one, white as all colors interfere constructively at the central band with color fringes. Right? That's what I mean by color fringes. Higher order fringes will see different colors with blue being deviated least, blue deviated least because shorter wavelength, red deviated most because of longer wavelength, and the other color in between. Right? So higher order, you won't see white anymore. Separation is more complete. Right? Basically, you can use this Huygens principle to help you understand when S1 and S2 are widened, this one and S1 and S2, remember they are point source from the same wavefront. Right? You widen it, basically allow more energy to pass through. So the band is brighter. Now remember when you widen the slit becomes further widening, the slit become point sources, normal point source. This one is normal point source. Right? There are point sources there, but they are not from the same wavefront. Not from this same wavefront, this one. Some of it, they are all different phase here, all the point sources. So they are incoherent. Thus, the bright band becomes blur and disappear. Okay, so far? Anything to ask? If not, let's carry on. Collimated. Collimated is narrow beam laser. Right, the one you're using, the lab one is usually called helium neon laser. Right, it gives red spot. Coherent, right? It's coherent. Doesn't matter where you send it. All along there, it will be always the same, the wavelength. The peak, the cross will be the same. Coherent. Monochromatic, that means it's only one color for laser. So we don't have to worry about using filter. Right? It's a laser, we use high voltages. So we do not look into the direct or reflector beam. The lens of the eye will concentrate the energy and damage retina. Right? That's why my lab assistant nearly gone blind. Because when we bought the laser, he turned it on, but it doesn't come on. Doesn't know that it has to take a while for it to work. Right? So don't direct it to reflective surface because it will be reflected and it may reflect to people's eye. Right? Like reflective surface will be like glass. The beam should be directed into a non-reflective surface. That means surface that is dark, painted, black color or black color. So when you do experiment, right, don't switch off the light. You want to do in that room, right? Well, lead there because your pupil will be wider, will be narrower. This protect against accidental damage to the eye in case there's accident. Okay, so you use laser, don't need to use a single slit anymore as long as it's perpendicular bisector there. So if your slit is horizontal, then you get your image horizontal. Just now we use the slit vertical, then we get the image vertical. Okay, must be able to play with what you learn. Okay, vertical there. Compared to previously. Right? Previously, vertical slit, we get vertical image. Question, explain whether we can obtain interference pattern with two lamps. Can or not? Instead of two double slit, we use two lamp. Can we get interference pattern or not?
Can.
Why? Yeah, why?
Because they are intersecting, then get
can't.
destructive.
You can't. The idea is they are not coherent source. Right? They are random. Right? Light sources, example, lamp is an incoherent source. both lambda are incoherent sources. That means they remember the filament is not point source. The filament is straight, got a lot of point sources there, and each of the point sources they emit at random. So whatever obtained here is not they don't interfere coherently anymore because these are not coherent source. So the interference will keep on changing, so you won't get interference. Right? How about this one? Where you can get for internet there? You use a light source. Can we get interference pattern or not?
Can, because it's only one coherent source.
No, cannot. Right? Even if it's monochromatic, remember it's not a point source. This is not a point source. Right? Filament is not a point source. Filament got a lot of different point sources, and each of them vibrate differently and give out light ray at different time. So they are not coherent. That's the reason why we need a single slit. No, light source, example, a lamp is an incoherent source. Such light falling directly on a double slit would not cause interference. Okay, so this one, this picture is obtained from the internet. Cannot, this is deceiving. Lamp is an incoherent source. Thus, light falling directly on a double slit would not cause interference. Right? You need a single slit or you need a laser. Single slit diffract the light so that the light falling on a double slit will be on the same wavefront. Right? You want a slit so that you want a point source. In a way, in a lamp, the wave arriving at a single slit are incoherent. Right? If you use a lamp, this one is very deceiving also. Right? The wave will be from different part of the filament. So it will come at different wave, come at different time. So they are incoherent here. Laser can. Okay. Okay, let's try some question. If you got your worksheet, it's on page, it's number 22. Okay, what's the answer? Water wave or wavelength 4 meter are produced by two generators S1, S2. Each generator, when operated by itself, produce wave which have amplitude A at P, which is 3 meter from S1, 3 meter, and 5 meter from S2, that's 5 meter. When the generators are operated in phase, what is the amplitude of the oscillation at P? Yep. Find the path different? Can? What's the answer? Can or not? Can or not? Didn't study or not paying attention? Answer is A. Path different? 5 minus 3 is 2 meter. How many wavelength is this one compared to the wavelength? Right? 2 lambda.
Not B, sir.
Say again.
Not B, You said A.
Oh, sorry. Why did I say A? It should be D. You are right. Sorry.
B.
No. Should be A because it's destructive interference, half lambda. Okay or not? Half lambda, you have to calculate the path. 2 meters is half lambda. Yeah, the wavelength is 4. So you must calculate the path difference. So your destructive inference is 0. A minus A. Okay, how about this one? Instead of 3 meter, instead of 5 meter, I change it to 7 meter. What will you get now? Yeah, find the path difference.
C, you'll get C. Answer C.
Right, path different. S2P minus S1P. 7 minus 3 is 4. 4 means it's one wavelength. Right? So one wavelength means constructive interference. So each of them is A. A plus A is 2A. Okay or not?
Okay.
Okay, calculate this one. I've given you the formula. Use your calculator, calculate out. 24. What's the answer? Find the wavelength of light.
$6.4.
Okay, let's see. Okay, your Y is that. Your lambda is what we want to find. Your capital D is 2 meter. Your small d, and small d, you have to change it to meter. No, what went wrong again?
Careless mistake, sir.
Cannot afford the carelessness. Okay, so it's high uncertainty because your Y is very small. Right? That Y is very small. Okay, what calculate again? What would be the fringe spacing Y if D is 10 to the power minus 6 meter? This is the slit spacing we use in diffraction grating for the same D. Okay, calculate again. Give me the answer. Same capital D, except that
Yeah, go back again, sir.
I'm just replacing this one. Sorry. Yeah, I'm just replacing this one to 10 to the power minus 6. This one. These two, I'm still using the same thing.
Yeah.
Sorry. Fringe spacing. This is the same. Sorry, this is the same. This is the same. I'm replacing this one to 10 to the power minus 6.
Okay.
What's the answer?
Go back to the next page. Okay.
Can get?
Yeah, 0.8.
Okay, you can see there. What's the difference if you use 10 to the power minus 6, right? Which is which we will study diffraction grating, there's the that D is very small. And you can see that is very large. But we can't get that. Only on the diffraction grating you can get that. Okay, what's the answer for this one? You want greatest. You want your X or your Y to be greatest. So what is the answer? Yep. Why it take so long?
Boy,
What's the answer?
B.
D, donkey.
Mm.
Okay, let's see. No, use this formula. You want this one to be large. Distance between slits, that's your donkey, must be large. Distance between, distance between slit, which is this one, must be small. Distance from slit to screen, that's a capital D. That one must be large. Right? Small, large. So it's either B or C. Then wavelength. Right? Wavelength must be long. That's why your answer is C. We are just using this formula to argue it out. Can? Anything not clear?
No, I don't understand, sir.
Understand what? Understand what? We are just using this formula only.
Oh, okay, understood.
Distance between slits is this one. This one must be
So
small.
it
You want
has,
this one to be large.
yeah, small.
Then distance between double slit, that's your capital D. That one must be large.
Large.
Then wavelength must be large. Sorry.
Answer C.
Wavelength must be long. That's why your answer is C.
Oh, okay, got it.
When light from two lamps fall on a screen, no interference pattern can be obtained. Why is this? Yep. What's the answer? Yep. What's the answer? This is the most important point. Coherent. Right? Coherent. The filament is an extended source. So the light emitted from the filament are all at random. There are many point sources there, but they are emitted not incoherent. Right? Different point source emit at no relation to each other. So if the two lamps, at a point there, if you have a lamp here, like what we did just now, right? a lamp here. Right? You take a point here. They are at random. They are random. That means the wave and the wave here, there's two waves, are at random. When they meet a point, it will keep on changing. So you won't see any pattern here. Right? Unless it is one wavelength and then they are coherent, and you see this bar won't be changing. Okay? Right? No point in going into a new topic. I think we will go to your checkpoint. Hoping you have done your homework. Okay, 23.3 from your book. Try this one. In Young's double slit experiment to determine the wavelength of monochromatic light from a source, the following measurements were made. Separation between double slit, distance of screen from two slits, 55 cm. Distance between the nth fringe and the m plus 10 fringe is 11.4 millimeter. Calculate the wavelength. Okay, what is the answer? Make sure after we learn the topic, you need to try the question itself. Calculate your x first or your y first. You're just using the formula, that's all. Y equals to lambda times capital D divided by small d or a. Right? That's your d, small d. That's a capital D. So that's the formula we're using.
4.15 times 10 to the power negative 12. Hey, wait, 1 minute. Wait. Sorry. 3.14 times 10 to the power negative 5.
Right? Write properly on paper and calculate it properly.
3.14 times 10 to the power negative 5 meter.
What's the unit?
Meter.
Wrong. You should know already. It should be 10 to the power minus 7. All right.
Wait.
There's 10 between these two. Between these two, there are 10 of them, so you divide by 10 to get your x. Then lambda is, right? Lambda, cross multiply, take the capital D down, you get that. Put in your value. Your x, this value, change to meter. I use cm. That D I change to cm. That one there, cm. Right? That capital D, all must be the same unit. You use meter, you use cm, all must be cm. Okay, the answer should be cm, not meter. Cannot afford carelessness. You lose unnecessary mark. Okay with that? Write down whatever you write down in your book. Okay,
Okay.
try this one. Same, you're just using the same formula. The figure shows the interference pattern formed on the screen in Young's two-slit experiment. The separation between the slit S1 and S2, S1 and S2. That's the S1, S2, 0.18 millimeter. The screen is 70 cm. From the two slits, that distance there, 70 cm. The distance y is 4. Y, that distance there. Bright one and bright one there. That's 4 millimeter. What is the phase? What's the phase difference between wave S1 and S2 at point P? Point P is here. Yeah. Dark band. What's the phase difference? Yep. What's the phase difference? Should be able to tell me straight away already. Why it takes so long? Phase difference here. What is this one? The first one. What's the phase difference for destructive interference? Yeah. Yeah, must know all this. Right? There's a lambda 0, phase different for bright one. Right? The next one is lambda, or this one, lambda. And that one must be half lambda. Right? This one must be half lambda also. Okay. Or I draw it differently. Here. Right? The first one is half lambda. This one is 1.5. This one is 2.5. That's all. Oh, sorry, you should have told me I forgotten to change the. Okay now. Yeah, just using this diagram, that's all. Phase difference is 0. The first dark one is half lambda. Right? The center one is 0. Path difference. Path difference is lambda. This one also lambda for bright. Right? This is the center one. This is the first one. This is the first one. And the first one for destructive will be half lambda. Half lambda. Right? So I've drawn it differently, that's all here. Must be able to label it. Right? That's half lambda, 1.5. The one is 2.5. Okay. Can? So what's the answer? Yep. A is what? Right? Make sure you know where is this is what? Right? D or A. That one is capital D. So this is right. This is you must know this is the center fringe. O is half lambda. Is 1.5. This is 1.5. Okay. That's what we get. Sorry. This is half. This 1.5. This 2.5. That's why we get 2.5 lambda. Calculate the wavelength of monochromatic light. What's your answer? Yep. What's your answer?
Yeah, wait, Archer.
Can or not? Can or not?
Yeah, just 1 minute, sir. Uh, 2.49. 2.49. The wavelength 2.49 meter.
Wrong. You can change your unit.
I change everything to meter.
How can be so small? Wavelength. Wavelength must be 10 to the power minus 7, must not roughly the magnitude. Should be about 400 nanometer, somewhere there. Or 10 to the power minus 7. Okay. Remember at P, they ask you your phase different. Phase different, path difference is 2.5 lambda. Phase different, lambda I must replace with 2 pi. Right? Lambda is equivalent to 2 pi. Then multiply is 5 pi radian. And at O, constructive interference. So no phase different, no path different. Right? Calculate your Y is given. That's your Y. Sorry. Yeah, 6.4, not 0.4, 6.4 here. So you calculate from here to here is 1. From here to here is 2. From here to here is 3. From here to here is 4. That's why you got 4x. Because 6.4. So divide your x is 1.6 and use the formula x 0.16. I use millimeter. Your D is in millimeter. And then capital D is 70 cm. Sorry, I've done something wrong. I've done something wrong. This one I changed it to cm. I got that one right. Yeah, this one I changed it to cm also. So that's why I get 0.16 and calculate out. Okay. Careless again. Unit didn't correct properly. Okay, now where you make your mistake, cannot afford all this carelessness. Any comment before we go to the last one?
No, check and stop here.
We finish the last one, C.
Mm.
What is the optical path difference between light wave from S1 and S2 at point Q? Path different, optical path different is the same thing. I usually call it path different, but usually your book will call it optical path different. Right? That's your point Q. Your point Q. Yeah. What's the path difference here at O? Yeah. What's the path difference here? You are not paying attention. On over with you already. Right? The center one is 0. So the path difference is 0. When it comes from the first one, path difference is lambda. Right? the nth order bright fringe. That one, the path difference is 2 lambda. So this is 0 path difference. This lambda is 2 lambda. So what's the answer for this one? What's the optical path difference between light wave from S1 and S2 at Q? Where is your Q? Okay, this is your 0 center fringe. Right? Diagram is slightly out lah. This is okay. That's your 0. That's your lambda. How different? That's your 2 lambda. Okay. Then multiply out. Right? Lambda is there. There's a lambda. Multiply out. Get that answer. Can or not? Anything not clear?
No clear, sir.
So if you don't tell me, Friday will be thin film. Okay. And as I said to you, the lecture is on YouTube. Go and download and listen, and then try out the focus if you are going to prepare well. You cannot hit and miss. As I say, you are wasting your parents' money if you're not putting in the effort. So if there's no question, I will stop here. Anything else you want to clarify?
No, sir. The Saturday class I can't make it, but then morning I'm so free. So Thursday, Friday morning can answer.
Thursday, Friday morning.
Yeah.
What time?
10.
10 o'clock.
Yeah.
Yeah, you want Thursday and Friday, but you are ready to do your homework or not?
Yes, sir, I'm ready, sir.
If not, it's just a waste. Every time I hear I've come to class, I have to scold you because you don't do your homework and make mistake in your calculation.
No, sir, I do, sir, I do.
By right, before I teach you, you should go over your book already, understand yourself. Then when I teach you, you force it in again. Then do homework to force it back in again. Okay, so Thursday, 9 o'clock, Friday, 9 o'clock, sorry, 10 o'clock. Then we go to thin film. After that, we go to diffraction. So if you've got no question to ask, then we will stop here. Anything else you want to ask?
No, sir. Okay. So see you on Thursday and Friday morning, sir. Okay, 10 o'clock.
Okay, we'll end now.
Okay. Okay, sir. Thank you. Bye.
Bye.